Hi everyone. So in this video, I will be discussing regarding exploratory factor analysis. The purpose of factor analysis is to describe and understand the correlation structure for a set of observation variable through a smaller number of unobservable underlying variable called the factor or the latent variable. These are thought to explain the values of the observed variable in a causal manner. Factor analysis is a popular tool in psychometrics where it for instance is used to identify the latent variable that explains people result on different tests, for example related to personality, intelligence or attitude. So we'll use the psych package along with the associate package gp annotations for our analysis. Let's install them. So I've already done that, and for our example we'll use the attitude data that comes with the R, right? And it describes the outcome of the survey of employee at a financial organization. So we can check the details regarding this data set. So it's a Chatterjee price attitude data, right? And if you want to see the data, you can just type it attitude. So there are 30 observation around seven different variables. So to fit the factor analysis models to this data, we can use the FA from Psych that required to specify the number of factors used in the model, and we'll get back to how to choose the number of factors, but for now let's go with the two, right? So let me load the library, and we'll fit the with the two factor. And so first thing is uh, FA does two things for us. First, it fits a factor model to the data, which yield a table of factor loading, that is the correlation between the two unobserved factor and the observed variables. However, there is an infinite number of mathematical valid factor models for any given data set. Therefore, the factors are rotated around according to some rules to obtain the factor model that hopefully allow for easy and useful interpretation. Several methods can be used to fit the factor models, and for rotation the solution. We'll look at some of the options shortly. So first, let's print the result showing the factor loading after rotation, and let me run this. And we'll also plot the result model using the FA dot diagram, showing the correlation between the factor and the observed variable. So let me run that. So the first factor is correlated to the variable advanced learning and the raise, right? And we can perhaps interpret this factor as a measuring the employee career opportunities as the organization. The second factor is strongly correlated to complaints, right? And and the overall rating, but also it is less degree correlation to raise and the learning and the privileges. So this can maybe interpreted as a measuring how the employee feel that they are treated at the organization. We can also see the two factors that are correlated. In some case, it makes sense to accept the factor to be uncorrelated. In that case, we can change the rotation method using the oblimin and to very max, right? Like this one. We run this, and let me run the again showcase the diagram. So here I'm using the ML as a setting for maximum likelihood estimation for factor model is proper under the assumption of a normal distribution of the data. So maximum likelihood estimation is widely recommended for estimation of factor model and can often work uh, well enough for non-normal data. So however, there are cases where it fails to find the useful factor, and FA offers several different estimation method. A good alternative is minors, which often work well when the maximum likelihood fails. So let's run that, and let me run the again showcase the diagram. Once again, the results are similar to what we saw before. In other example, the result differ more, and when choosing which estimation method and the rotation to use, bear in mind that in an exploratory study, there is no harm in playing around with a few different methods. After all, your purpose is to generate hypotheses rather than confirm them. And looking at the data in the few different way will help you out to do that. And to determine the number of the factors that are appropriate data set, we can draw a scree plot with scree. So this is interpreted in the same way as the principal component analysis. Let me do that, right? So we look at the elbow in the plot, which tell us at which point adding more factor no longer contribute much to the model, right? So after I think two is there is no much contribution. A useful alternative version of this provided by FA parallel, right? And which adds the line showing what the scree plot would look like for randomly generated uncorrelated data of the same size as the original data set. And as long as the blue line, let me zoom it here. So as long as the blue line representing the actual data is higher than the red line, right? Representing randomly generated data, adding more factor improves the model. So let me close this. And some older tests recommended that only factor with the eigenvalue, which is at the y-axis, right? Greater than one be kept in the model. It is widely agreed that this so-called Kaiser rule is inappropriate as it runs the risk of leaving out important factor. Similarly, some older texts also recommend using the principal component analysis to fit factors model, while the two mathematical similar in that both in some sense reduce the dimensionality of the data. PC and the factor analysis are designed to target different problems, and factor analysis is concerned with an underlying causal structure where the unobserved factor affect the observed variables. And in contrast, the PCA simply seek to create a smaller number of variables than that summarize the variation in the data, which can work well when there is no unobserved factor analysis affecting variables. So this is what we have for the factor analysis. We'll move to uh, we'll see different topic in the next video. Thank you.